In this video, we're going to discuss two optimization problems. One is about finding minimum manufacturing cost, and the other is about finding the minimum construction cost. Let's start with the first problem. An engineering department is designing a rectangular box with a volume of 640 cubic feet and a bottom whose length is twice its width. If the cost per square foot for the bottom is 25 cents, for the top is 12.5 cents, and for the sides it's 5 cents, what dimensions will minimize the cost? Let's draw a picture of the bags that we want to manufacture. So we want to manufacture a box with a bottom base whose length is twice its width. So if we let the width to be equal to x, then our length will be equal to 2x. And let's say that the height of this box is equal to h. Solving optimization problems may be divided into two steps. The first step is to write your objective function in terms of a single variable. When we say objective function, it's the quantity that you want to maximize or minimize. In this case, we want to minimize the cost, so that is our objective function. It's the cost function. And we want to write that in terms of a single variable. Of course, if you are in single variable calculus. And we should also determine the domain that we want to consider for our variable. And the second step is to apply maximum and minimum principles to find the maximum or minimum value of that objective function. So let's apply that procedure in solving this problem. The goal of this problem is to find the minimum cost. So we're given different cost per square foot for the bottom, so that is 25 cents per square foot for the top, and then for the sides. So let's try to write down the cost in terms of a single variable, okay, as a function of a single variable. So here we have the area. The area of the bottom is, of course, 2x times x, so that is equal to 2x squared. And since the cost is 25 cents per square foot, then the cost for the bottom of this box will be 25 times 2x squared. Now, the top also has an area of 2x squared. And since the cost per square foot for the top is 12.5 cents, then the cost for the top of this box will be 12.5 times 2x squared. Now, let's look at the total area of the four sides. Okay, so here we have the front face and then the back face of this box. So the area of this front face will be 2x times h, and then that is times 2. So plus the back face, you'll get this total area, which is 2 times 2hx. Now, this right face and left face have the same area, and the area is h times x. So times 2 will get 2 times h times x. And since the cost per square foot for the sides is 5 cents, then the cost for the four sides is 5 times this expression. Now let's simplify this a little bit. So we'll get here 50x squared, and then this one is equal to 25x squared, and this is 5 times 6hx, so that is equal to 30hx. So we combine these two, we'll get 75x squared plus 30hx. Now, the first step is to write our objective function as a function of a single variable. So we still have here h and x. So we need to write this in terms of x only or h only. So how do we do that? Here we have an additional information that the rectangular box should contain a volume of 640 cubic feet. So from this information, we can write this volume here, which is equal to 640 cubic feet, as 2x squared h. So that is length times width times height. That is the volume of this box. And it must be equal to 640. So therefore, we can write our h in terms of x, and that is equal to 640 divided by 2x squared, that is equal to 320 over x squared. So now we replace this h here by this expression, and we'll get 75x squared plus 30 times this expression times x. So now we're able to write our c as a function of a single variable x, and it is equal to this expression. So I factored out the common factor 15 so that we can easily differentiate this later. And what is our domain here for the variable x? So since the volume must be equal to 640, x cannot be equal to 0 in this case, because if x is equal to 0, the volume will be equal to 0. So our domain is x greater than 0. Let us now find the x that maximizes this function here. So since the domain is not a closed interval, we cannot use the closed interval method. So we can only use here the other maximum minimum principle, and that is actually the first derivative test or second derivative test. So take note that if there is only one critical number, then from the first derivative test and second derivative test, our conclusion will be absolute extremum. It's like absolute or global minimum or absolute or global maximum. So that is true only when you have a single critical number in your domain. So in this case, so we look for critical numbers first for this function. So we take the derivative. So by definition of a critical number, it's an element of your domain where the derivative is 0 or does not exist. So we compute for derivative and we'll get here constant. We just copy the constant, and the derivative of this expression is 10x. And then just think of this one as move the x here as x raised to negative 1 so that you can easily take its derivative. So the derivative of this one will be negative 640 x raised to negative 2. And you may write that as 640 over x squared. Now, C prime doesn't exist only when x is equal to 0, but x equals 0 is not part of our domain, so therefore that can't be a critical number of C. So to find the critical numbers, we just equate C prime of x to 0, and this is equal to 0 when this factor is equal to 0, then that means this 10x is equal to 640 over x squared. So we have here 10x equal to 640 over x squared. Cross multiply, we'll get 10x cubed equal to 640. Divide both sides by 10, we'll get x cubed equal to 64. And then taking cube root of both sides, we'll get x equal to 4. And this is the only critical number of C. So therefore, if we're going to apply first derivative test or second derivative test, our conclusion will be not only a local minimum or a local maximum, but it will be a global or absolute maximum or global or absolute minimum. Now, how do we determine whether this critical number will give us absolute max or absolute min? So we look for the second derivative. So the second derivative of this one, so taking the derivative again, so we'll get here 15, just copy the constant, and the derivative of this factor is 10 and then plus 1280 over x cubed. So it is clear that for any x greater than 0, our second derivative is always greater than 0. So that means by second derivative test, since c prime of 4 is equal to 0 and c double prime of 4 is greater than 0, By second derivative test, you have a local minimum at x equals 4. But since 4 is the only critical number of C, we are sure that this C of 4 is the absolute minimum. So therefore, C of 4 is the minimum cost. So our answer to this problem, since we're looking for the dimensions that minimizes the cost, so the dimensions that minimize the cost are our length, which is equal to 2x, so that is equal to 2 times 4, so 8 feet, and then our width, which is actually x, that is equal to 4 feet, and our height, which is 320 over x squared, is equal to 20 feet. If you're looking for the minimum cost, then you just plug in this x value into your function to get the minimum cost. Moving to our next problem. So here a church is located 10 miles east of a school and 5 miles south of a hospital. An engineering department is planning to construct a new road from this school to the hospital by restoring a section of an old road between the school and the church, and then only a section of this, and then joining it to a new road to the hospital. So if it cost $100,000 per mile, okay, for restoring this old road here, and it cost $300,000 per mile for constructing a new road, how much of this old road must be restored to minimize the construction cost? Now, let's represent this section to be 10 minus x. Actually, we can represent this by x, but I prefer it to be 10 minus x so that I can get a simpler expression for this length. So if I represent this to be 10 minus x, then this section here is equal to x because the distance between the school and the church is 10 miles. Okay, now what is our goal? We want to minimize the construction cost. So our goal is to minimize cost. And what is the construction cost here? So we need to find the cost for this section plus the cost for this new road. Since the cost for this section is $100,000 per mile and the cost for this new road is $300,000 per mile, then the total construction cost will be $100,000 times 10 minus x and then plus $300,000 times square root of 25 plus x squared. Now, what is the domain under consideration here for our variable x? It is clear from our diagram that x must be between 0 and 10, inclusive of the endpoint. So x is greater than or equal to 0 and less than or equal to 10. So x equals 0 means that the road will be constructed from S to C and then C to H. Now, what does x equal to 10 means? X equals 10 means that we construct directly the road from S to H. Since the domain of our function is a closed interval, so take note that this function here is continuous on the closed interval 0 to 10. So therefore, we can apply closed interval method to find the absolute minimum of this function. And we can also apply actually the first or second derivative test to find the value of x that will minimize this function. Let us now find critical numbers for this function because both maximum and minimum principles require us to find the critical numbers. So we have to compute for the derivative of this function here with respect to x. And the derivative will be equal to, of course, this will be 100,000 times the derivative of this, which is negative 1. So that is negative 100,000. And then plus we just copy this constant factor here, 300,000, times the derivative of this. We apply extended power rule. We bring down the power, subtract 1 from the power, so that is 1 half minus 1, so that is negative 1 half, times the derivative of this base here, which is equal to 2x. And we can cancel here the 2 and then this 2, and we can factor out the negative 100,000. Again, the goal here is to easily find the critical numbers later. So we factor out the negative 100,000, and we'll get here positive 1, and then you'll get minus 3x over, this is written in radical form, square root of 25 plus x squared. Now, this c prime of x, because of course the denominator will never be equal to 0 because x squared is always greater than or equal to 0. So the only critical numbers of this function c here is what? Okay, the values of x that will make this equal to 0. And this is equal to 0 if this is equal to 1. So therefore, we have here 1 equal to that expression, and then we cross multiply, we'll get this expression, and square both sides, we'll get 25 plus x squared equal to 9x squared. And then we'll get here 9x squared minus x squared. You'll get 8x squared equal to 25. Dividing both sides by 8. And then taking square root of both sides, we'll get x equal to 5 over 2 square root of 2. So here you can already use the closed interval method to determine the x value that gives you the minimum cost. All you need to do is to find the value of this c at these x values at the endpoints 0 and at 10, and then at this critical value, and compare the function values. Okay, so but we can also apply second derivative test here to determine whether this critical number, which is the only critical number of this function, so if this gives us the local minimum, then we are sure it's the absolute minimum of this function c, because it's the only critical number of c. So if we're going to apply second derivative test, we have to compute for the second derivative of this function. So the derivative of this one is equal to 0, and for the derivative of this second term, we use derivative of a product. So we'll get here, so we think of this one as a product of this expression times 300,000 x. Okay, because 2 times 1 half is just 1. So using derivative of a product, it will be equal to this expression times the derivative of 300,000 x with respect to x. So that is 300,000, and then plus 300,000x times the derivative of this expression. So again, that is equal to, bring down the power, negative 1 half, subtract 1 from the power, so that is negative 3 halves, and then times the derivative of the base, which is equal to 2x. And we can write this down in this form, okay, making the powers positive. And then when we factor out this expression, 300,000 over 25 plus x squared raised to 3 halves, then we can write the remaining factors as 25 plus x squared and then minus x squared. Now, as you can see from this one, x squared minus x squared is just equal to 0. So therefore, the c double prime here, the second derivative, is always greater than 0. Okay, so since the value of the derivative of this critical number is equal to 0 in this case, and the second derivative is positive, so by second derivative test, we have a local minimum. But since this is the only critical number of the function, this local minimum is an absolute minimum. So therefore, this value here, function value, is the minimum cost. And what are we looking for? We're looking for the what? Number of miles that we have to use for this old road. Okay, so therefore our final answer will be the construction cost is minimized when this 10 minus x, so we found already the x, so that is 10 minus 5 over 2 square root of 2. This is approximately equal to 8.23 miles of the old road is restored. So therefore, we need to restore here 8.23 miles and then construct a new road from that point to the hospital to obtain the minimum construction cost.